So in this video, we're going to be talking about the different characteristics of the different parent functions that you'll deal with in this chapter. So the first thing that we're going to go through and recognize is their names, their equations, and their graphs, but we're also going to add in some details of things that you might notice along the way. So starting very basic, we're going to start with what we call the constant graph. This is a graph that would have an equation where it's like y equals and then just a number, so we'll call it a for now. Now this graph will have a flat line shape, something like this. The convenient part about it is that right there, the graph crosses the y-axis at a. So the constant graph would be y equals some number, so that'll be just a number with no letters. So it'll be like y equals 4 or y equals -3. And the graph will be completely horizontal. It will not have any sort of slant to it whatsoever. Second type would be called linear. Now this is something you should be super familiar with by this point. The parent function of that would be just y equals x. Now when we talk about parent functions, don't forget, parent functions are the most basic form of that equation. Once we start to look at more challenging versions, you might see a slope, you might see a y-intercept. There could be a lot of different things that you see added on to this. So the parent function y equals x would have this sort of shape. Still a perfectly straight line, but now it's at a diagonal of some kind. Now that diagonal does not always have to be this steep. It could be a very shallow line, or it could be very, very steep, even more steep than this. So things that you would be looking for to recognize a linear function would be, like I said, just that x, the straight line. So you'll be looking for x or a number times x. Third on our lineup would be quadratic. So quadratic equations are a little bit different than linear in that they have an exponent. You will always see some sort of multiplication between x's in order to make this happen. So a quadratic graph is going to get this kind of unique shape that looks like this. And what you'll be looking for is an x squared or an x times another x. So it could be like x plus 1 times x plus 4, or it could be just an x squared, or it could be like an x minus 5 squared. Next up would be absolute value. This is the most interesting graph in my opinion because it has a very different shape to anything that we really spend a lot of time looking at. It also has a unique equation because these symbols right here, these two vertical lines, mean absolute value. You don't see that in any other type of graph that we deal with in our classes, algebra or algebra 2. And it has this very specific V shape. Again, it could have a slope where the V is really skinny, or it could have a really wide slope where the V is really wide and short. But the most unique piece of this is those vertical lines and that it's perfectly straight V-shaped. It is not at all U-shaped like the quadratic. It's completely straight lines with some sort of vertex here in the middle. So it must have those straight lines. Next up would be exponential. So I notice a lot of students tend to have trouble recognizing the difference between an exponential and a quadratic, mostly because they both have exponents in them. But the difference here is that an exponential will have some sort of base taken to the power of x. So the x will always be in the exponent of an exponential graph, where in the quadratic, it's a number up here, it's a 2. So the difference is going to be where your x is placed. Now this graph would look like this. So it's not U-shaped, it's kind of L-shaped-ish. What you're looking for is a flat side on one side, and then the other side to be going up very quickly or going down very quickly. So exponential graphs are unique in that they have the x in the exponent. Next up on our list would be a radical graph. Now, radical graphs depend on the type of radical that you're looking at. So the parent function we're going to use is the square root of x. Now, the cube root of x will look a little bit different than this, but they follow the same basic patterns. So the radical parent graph looks like that. Now the unique piece here is that every other graph, as you've probably started to notice, has never-ending pieces. It goes in both directions forever, arrows on both ends. The radical graph does not. Now, like I said, the cube root graph looks a little bit different. But for the square root graph, it has a definite starting point and it continues on from there. So it has a square root symbol or a multi-root symbol where there's a number up here. And that's what makes it unique. Moving on, the next one would be our rational graph. Not to be confused with a radical. A rational is an equation with a fraction, where the x is in the denominator. So this graph actually looks a little bit like the exponential, just a little. But it's different because it has two pieces to it. So a rational function has x in the denominator of a fraction. So x is in the denominator, and it has two pieces of the graph. You'll notice none of our other graphs so far have been broken into two different pieces. Just the rational graph has that. Next up will be logarithmic. If you are new to these topics, logarithmic might be an unfamiliar word to you. It is a type of graph that you will start to deal with throughout your time in algebra, algebra 2, where it's y equals log with a base x. So log is kind of like an operator on x, which you will learn more about later. This graph looks super similar to the exponential, which you'll find out why once you start to delve into logarithms. That's a little messy. Let's try and reorganize that a little bit. There we go. So it looks almost identical to the exponential, except that it's been flipped over. There's a reason for that. But the exponential or the logarithmic graph, the reason that you'll be able to recognize it is it will have that log phrase in it. So it's absolutely impossible for us to draw one, at least for as far as we're going to talk about, where it would not include the phrase log. The final one that I'm going to add in here is called a conic graph. Now, conic graphs vary fairly widely, but the piece that's kind of unique here is that we see an x and a y squared. So I'm going to further specify and say circle or ellipse here. Now these graphs will form, obviously, a circle or an ellipse. So the unique piece for us here is that we're going to see that multiple squared going on, where there's not just an x that's being squared, but both x and y are squared. Okay, so we've gone through and we've recognized the different types. So something that I like to do to make this make a little bit more sense in my brain is make notes of things that look unique here, of what am I looking at in the picture that would help me figure out what I'm looking for. So in this graph, the constant, we said it was a flat line, completely flat. It's not going to have any tilt to it whatsoever. Where a linear line is similar to a constant, but it's a tilted line. Quadratics will always be some sort of U shape, where absolute values, though they appear similar in my drawings here, are V-shaped. Exponentials will have a horizontal tail, and when I say that, I'm referring to this side that's kind of flat over here. Radicals, if you're dealing with a square root type radical, will have a starting point. If you're dealing with a cube root, it'll have a slightly different appearance at that point. Rational graphs, they have two pieces. Logarithmic graphs, similar to those exponentials, except they have a vertical tail. And then conic, focusing on the circle and ellipse type, will have a circle or oval type graph. So those are our 9 parent functions. There are more parent functions out there that we're not talking about here, but these are the 9 that we're going to spend the most time focusing on.